Thanks, Matt. So before I hand it over to George, I'm Dag Liodden. I'm the CTO and co-founder of Tapad, and I'll start with today's first poll. A lot of questions, or a lot of people have talked about data, but no polls here today. So let's start. Who has purchased anything online on a computer? Raise of hands. How many have purchased anything on a mobile device? About the same. So how many did research a product on a mobile device and then purchase it on a computer? Still just half of it. To make it a little bit more interesting, how many people has seen an advertisement on a television, picked up their phone to do research on that product, and then purchased it on a computer? Yeah, actually still quite a few people. But most marketing technologies today have a really, really hard time to capture this kind of behavior. It is impossible for most marketing technologies to be able to take information that is captured on one device and make that actionable on a different device and then measure the results after that. And this is the core of Tapad's business in marketing technology. Is what we call the device graph, which connects the different devices that a user uses in his everyday life in an anonymous fashion and makes that available for advertising, targeting, analytics, as well as all other sorts of marketing technologies such as content optimization and personalization and so on. So without further ado, George Gemelos, who's our head of data science, will take you through how we do that.
Thank you. So actually, I'd like to go through just a recent experience we've had. So I think we've all probably solved the problem and then been forced to revisit that problem a few years later. And what we encounter is that when we first started to attack the problem, we probably made some very quick design decisions. And then it has a purpose. It helps you really quickly narrow down the solution space, tell you what solutions might work out, and kind of focus you down that path. They often reflect our resources of time and our priorities. So what happens to these decisions when we revisit them, let's say, a year, 2 years later? Well, we'll find that we sometimes have thought about that initial decision so much to be part of the problem that becomes a part of the problem statement. And we often forget that it was an option when we first started to attack this problem. And what's worse is that most likely all those assumptions are now wrong. And so you're stuck trying to solve a new problem in a very limited way. And I think one of the key examples here is, do I do an online or an offline type of algorithm when I first attack a problem? Do I want to do this in a streaming fashion or a batch fashion? And we encountered this when we were dealing with our device graph. And here's probably my only visual of the entire talk. So a device graph, you can think of it as a way representing that connectivity that Dag was mentioning. A vertex will represent the device, and an edge between two vertices will represent our belief that, depending on the device graph, that if it's an individual device graph, that these two devices are owned by the same person, or if it's a household device graph, that they belong in the same household. And in terms of scale, we're about 1 billion devices in the device graph and 600 million edges. And how do we make this device graph? What's the input to this? Basically, sightings. Really simple things. They have 3 types of categories. You saw a device at a particular IP at a particular time, saw a device at a particular website at a particular time, and maybe you saw an app active on a device at a particular time. And the scale of these sightings at the time we first might attack this problem is about 2 billion sightings per day. And you say, okay, I have this problem. Do I want to go offline or online? And let's go through the pros and cons real quick. This is the way we thought about it at the time. So online, if you think of all the pros and cons of online, it's computationally fast. You really have to keep up with the data. Everything you do must be done as soon as that bit or signal goes past. It's space efficient. Technically, you don't have to store anything. You might have to worry about state space, and we'll think about that a little bit later on, but no real storage constraint. It's algorithmically limited. You can do everything you want in a streaming fashion as you could if you had all the data sitting in front of you. Some people have put a lot of work into making that limitation go away, but it's still always there with us. And offline, well, it's algorithmically unlimited. If you have all the time in the world and all the space in the world, you can do whatever you want. Unfortunately, space and complexity become an active constraint, and that was kind of the motivator for us. We're saying, okay, do we want to store all these sightings? Do we want to have to build our device graph in some batch form, let's say in one shot? And that seemed not the ideal solution. So we're like, let's try the online approach. And if we go to online, we have to deal with the algorithmic limitations. There are certain things you might want to do if you're building your device graph and you're processing these sightings that you just can't do in a streaming fashion. And I think a simple example will be trying to process IPs while building your device graph. And give you an example. If you see a sighting come in, you might want to treat it differently if you think that it's coming from an IP that's a home IP, or a carrier IP, or maybe a work IP, or maybe a cafe in your neighborhood. You probably wouldn't want to use the same models for all of them. But if you're streaming your data, you probably have to have some sort of classification of an IP ahead of time. And that automatically forces you to separate these two problems. And that's not always the best thing to do. But maybe if we do an offline classifier on IPs, we use that at real time as we're streaming our data, we can get around this. And that's the first thing we attacked, and it seems to work pretty well. Then comes the idea of state space. So we mentioned that online process, really don't have to worry about storing data, but you do have to worry about state. And what do I mean by state? So the sightings you're seeing are very basic. It's like I saw this device at a particular place. What if you want to start building a path? You want to say, well, I want to see how this device goes through IP space, web space, app space, and I want to start building this path and use this path to compare devices. And maybe I want to make this path transitional in terms of time. I can slide time back and forth and just try to compare devices based on their path. Seems like a great idea, probably one of the first things anyone would think about. But now you can start to think about how much that state space is quite complex. You're dealing with a lot of things, and you're dealing with a huge history. And now you're trying to store all this and get very fast access as you're classifying in real time. So you're like, okay, that's not going to work. It's going to explode, and now there's no way on a billion devices I'm going to be able to build that. So you try to project that down into some sort of really small dimensional space that's very quick to access. And you try to do that trade-off between what can I store in real time and what can I possibly get the best use out of. And that was actually a big part of the stuff we worked on at first. And then the last one I think would be kind of like the indirect parameters. So if we discuss a device graph, you probably already start to think about what it should look like, right? I mean, particularly let's look at an individual device graph. It's not a social network. It's not truly very much connected. It's a bunch of small subgraphs, each one representing an individual. So if I showed you a device graph and there was a 10,000 node connected component, you'd be like, that's a bit odd. You know, that person has a real fetish for their devices. And so you'll say, maybe I don't want to do that. So how would I stop that from happening? Maybe I'll say, okay, if I'm building this graph past, let's say, the 50th device or something, I'm going to start putting an exponential penalty on each edge you try, each device you try to connect to that component. Sounds like a great idea, but let's see if we can implement it in a streaming fashion. You see this data coming in, you're modifying your device graph, and somehow you need to know what your connected component is. That implies you're doing a connected component analysis in real time as you're processing your device graph. That's pretty impressive because on a billion node device graph, it could probably take days to process. So you don't have access to a connected component analysis. What else can you do? You're kind of left to do some sort of, say, secondary effect. Maybe take an individual and say an IP address is kind of like a proxy for an individual. Each individual comes from an IP address. Start to do some sort of maybe blacklisting or weighting on signals as they come in from that IP, and you start to get good behavior that way. But it's still not what you really want. But it turns out you do all these things, and it works, and you have a device graph that is extremely good. It's very accurate, and a billion nodes, 600 edges. So why revisit it? And for us, it was scale. We wanted to just take the device graph, make it 3-4 times larger, and we were saying, how could we do this? And we started this problem a few months ago. It was like, well, where do I start? Do I start on the online approach? What can we do with the online approach? And quickly it seemed, maybe we need to go back and revisit that decision. Thinking about all our new priorities here. So if scale is your priority, that kind of means you are going to have more data. And we're going to have now, instead of 2 billion sightings per day, anywhere from 20 to 100 billion sightings per day, seeing about 1 billion devices a day. So now you're like, okay, maybe I'll still stick with streaming. Problem with streaming is that you don't have to store this data, but now you have to process it in real time, and that becomes quite daunting. Trying to process, say, 100 billion sightings in a day in real time, modifying a single object is not quite an easy thing to accomplish. And then besides getting the more data, you might say, well, I want to make the most use of my data I possibly can. And for someone like myself, that means I want better models, more complicated models. And maybe I even want to get really noisy data that I know is not perfect, but I can clean it. But I can't quite do that in real time. And that means algorithm limitations become a big factor. And besides having all the infrastructure for online, kind of forced us to say, well, maybe we should reconsider offline, as probably non-intuitive as it was for us. So if you do offline, you have to kind of go back to the two major constraints. That's space constraint and complexity. So with space, you're dealing with, say, 100 billion sightings a day. You want to keep 4 months of data. It's about 12 trillion sightings, coming in at about a terabyte an hour. That's pretty big. We do have some gains over the past couple of years since we've had the first device graph, and that is, well, we have more resources, we have more space, and we have new technology like my favorite thing, the Parquet file, able to compress the data more, column read it, so it's a little bit faster to read for if you want particular segments of data. But that's not going to get you all the way. So you're left with the idea of I still need to project my data down to some sort of simpler space. And we're loath to do that as data scientists. I never like to lose information. So you spend a lot of time figuring out what can I do to this data that allow me to still have maximum generality in the future, but reduce it to a point where it's sizable. And not only just sizable, where I can go out and start buying more data or collecting more data in the future, envision having 2x, 3x, 4x the amount of data I have right now. So that was the first thing we did, because if we couldn't accomplish this, there was nothing we could do. And then complexity. If I give you 12 trillion sightings and a computer and I say, go at it, have fun, give me a device graph, I would like this process to finish within a day maybe even sooner, because I'd like to build this graph on a daily basis. So if it takes 2 weeks, it's not a feasible solution. So what we do here is say, if you want to ensure that a team of 5 people working on this problem do not diverge away from the space of solutions which are truly computationally feasible, it's a good idea to start thinking about what are the barriers to that. And we do that for us. It was breaking down the problem into what I think are really fundamental blocks that you had to address this problem. Things like, well, we do know that somehow we need to combine IP and bridging. We need to somehow do a joint modeling of that. We know that we might want to start taking into account pathing, complexity space. And how do we ensure that we can do that but still maintain the complexity constraint that made this work out? So we did that and allowed us to start exploring a nice space. And at the same time, we threw in testing, because testing on an online algorithm is not a deal. It's pretty hard. Whereas in an offline batch process, it's nice to go through and just be able to crank through different models and try that. And what we found was, when we were done with this process, and this process actually has worked, we're about to launch our first batch graph at the end of the month. We have about kind of intermediate results, about 18 days worth of data. And we wanted to compare it against our device graph. So our device graph has been running it's online, so it's kind of hard to say, but you can think of it as months worth of data. And we're going to compare it against just 18 days of batch data and see what it looks like. And what we found is that we took the number of connections, called the density of our graph, from 6 million edges to 1.6 billion. And our accuracy stayed roughly the same. And here we measure accuracy. We have a third party come in that has what we call deterministic data in the industry, which is they have login data on various devices, and they can create these deterministic bridges. And they come in and audit our graph on a regular basis. So we found that it's a pretty good model here. And what I like about this is that I think if we went back to the original problem of saying I want to revisit the device graph and think about scale, it was not my first instinct to go to offline. I don't think anyone wanted to do it. It means kind of scrapping a lot of our infrastructure and restarting it. And I think there was a lot of talk of just sticking into a kind of a streaming fashion. But I think we would have been bashing our head against the wall trying to get a 10, 15, 20% gain, maybe 50. But we would never have gotten a 3x or 300% gain as we receive now, with the ability in the future to just add on data very easily and try out different models. So, sometimes it's very nice to step back, see the problem for what it is, take away all the assumptions, and look at the open box again. That's our experience.
Thank you very much. In the interest of time, let's switch to questions directly. Oh, the questions right before the drinks. Andrew.
Hi, my name is Mike from Run. I'm curious to hear about what sorts of algorithms you're in particular able to leverage offline that you couldn't do online?
Sure. I think the key example would be IP classification while doing bridging. So, like I said, if you're trying to classify an IP and you are using a signal to bridge on, every IP gets its, let's call it its maximum likelihood classification. Now, that's not what I'm really trying to do. My problem is not classify IPs and then bridge. My problem is, given all this data, what's the maximum likelihood graph that describes it? And that might mean that sometimes for a particular device, you give a classification of a home IP to that device. But in a different device, you might call it something else. And it's kind of counterintuitive, but if you put weights on things, it will actually work out much better than trying to make it kind of an absolute. Saying this is absolutely home IP, that kind of leads to more to errors creeping into a device graph, where softer information is a little bit easier to deal with.
Great. One more over there.
I'm sorry, I couldn't really make out
Yeah,
the
I
question.
think the mic is off or something.
Hello, can you hear me?
Yes.
Okay. So I think the question which was asked was, what kind of algorithms are you using for this device graph, which is basically the probably center of your technology and how you identify the devices which are connected. I mean, UID will give you just the ID of the device, IP will also give you, but who's using it? How do you decide that?
Sure, we never really try to resolve the actual user from the device. All we care about is the relationship between the devices. So our use case is often, given device, say this iPhone, what other devices is it connected to? And that statement is slightly different than actually talking about an individual. It never says, given this individual, what devices do they own and use? And I think that kind of separates from first of all, it's a little more privacy safe, and it separates the problem from trying to actually tie a device to a physical person. I'm sorry, did that answer your question?
Yes, but I also asked about the device algorithms which you are using.
Sure. So in terms of algorithms, well, first of all, as this is basically in a research phase, we do have our candidate first release algorithm. There are many basically competing algorithms in-house. We have everything from various methods of classifying IPs, from random forests to take nearest neighbors. We have, for the actual pathing, we have algorithms that focus more on, let's say, and we have many algorithms that focus on pathing and different types of dimensionality there. I could go a little bit more detail offline, if you'd like.
Great. And one last one.
Is this on? Yes. My name is Amir. I work at Morgan Stanley. I just wanted to know, where do you get the data, and also that third party that has deterministic mapping? Like, who would have that data, and also how do you get the data?
Sure. Data can come many ways. You can buy it from third parties. It comes across on ad exchanges very often as well. In terms of the third party, you probably can think on top of your head many companies that have login data, where you're logging onto your phone, onto your laptop, onto your browser, and they have that data in-house. Whether they choose to sell it or not, that's depending on the company. We're actually putting out a report from our third party. It's a reputable company. It will come out at the end of October that states these accuracies. But there are many companies that have it. I'm sure you can think of one with a G. Google's has one.
All right, that's all of the time we have. Thanks, George.
Thank you.
And thank you, Dag. Appreciate it.